Okay, so now we can talk about the dissociatively activated mechanisms. So these are mechanisms of ligand substitution reactions of metal complexes in which dissociation is the RDS, the rate determinant step. And so remember, we have three broad classes of mechanisms: dissociative, associative, and interchange. And all of these can have different flavors. If they are the dissociatively activated flavors, they'll have different RDSs, right? So if you have a dissociatively activated dissociative mechanism, the RDS is going to be dissociation, that first step where the X just leaves and you get a lower coordination number. If you have a dissociatively activated associative mechanism, it's going to be the second step where the X group leaves from the higher coordination geometry to form your product. And if you have a dissociatively activated interchange mechanism, it's going to be the second step where this transient species loses its ligand to make the product. All right, so we call these three different types of mechanisms DD, AD, and ID for short. So for dissociatively activated mechanisms, doesn't matter which of the three, the reaction rates are not going to depend strongly upon the nature of the incoming ligand. This makes sense and is the opposite of what we saw in the last video about associatively activated mechanisms, right? Because the rate determining step isn't dissociation, and association is what is controlled by the incoming ligand, right? And so you can look at these reactions with these nickel complexes with ammonia versus pyridine, and they're about the same rate. You know, they'll vary a little bit, but they're about the same rate. Most reactions with octahedral complexes are dissociatively activated. Contrast that with most reactions with square planar complexes being associatively activated. All right, so what does the reaction coordinate look like for a dissociatively activated dissociative mechanism, DD? It's going to look like this, right? Where your rate determining step is the dissociation. So this is wrong. Sorry, guys. the circle there is wrong. Sorry about that. So the circle should be on here. Okay, not there. The RDS is this one. And that means this first bump, that's where this first transition, right? That's where you have the dissociation occurring in a dissociative mechanism, right? And then once you've dissociated, you do the second step. This is the fast step. Okay, this is the fast step. That's dissociation. And so that's going to have a relatively low activation barrier. And because of that, once you form the intermediate, it's going to very quickly react to go and dissociate and make the to associate and go and make the product. So because the intermediate quickly reacts, because this reaction barrier is very low, that means that you are not going to be able to, in most cases, detect the intermediate. All right, so if you have a dissociative mechanism where you can't detect the intermediate, that's pretty good evidence that you have a DD type reaction. And how could you tell it's a dissociative mechanism? Remember, that the fact that it's dissociatively activated would come from it not having a strong dependence on the incoming ligand. All right, next one, here we go. This one is correct. So this is a dissociatively activated associative mechanism. So I have the RDS in the correct spot here because it's dissociatively activated. So for an associative mechanism, this is where the dissociation of the associated complex is where the RDS is going to be if you're AD. And so your reaction coordinate is going to look like something like this, where your second step has a very high reaction barrier. That's going to trap the intermediate and make it relatively long-lived, enough that you might be able to detect it. So if you can detect it and you know you have an associative mechanism, that means you have a dissociatively activated associative mechanism. And then you also have the dissociatively activated interchange mechanism. Interchange mechanisms don't have any RDSs, but you would have a higher reaction barrier for the second step, but there's no intermediate to detect. And it's pretty hard a lot of times to tell whether or not you have an interchange mechanism or not.